Welcome to Data Science with EJD. In this video, we'll be looking at decision trees, still on the classification algorithms in supervised learning. In the previous one, we had seen k nearest neighbors, where we get to classify based on distance. Okay, so in this case, we look at the table of contents. We'll be looking at introductions to decision trees. Then we'll look at tree construction, recursive partitioning and splitting criteria. Then we'll look at entropy and information gain. So then we'll look at entropy, information gain, and other criteria like Gini impurity, ratio. Then we'll look at stopping criteria and overfitting. Then we'll consider pruning, talking about pre-pruning and post-pruning. Then we'll look at decision tree algorithm summary, building and visualizing the decision trees. So we have a Python coding example to explain that. So we'll build a decision tree and we'll also visualize it. Then we'll look at the interpretation and limitations of decision trees. All right, so we're at that point where we look at introduction to decision trees. A decision tree is a supervised learning algorithm used for classification. It can also be used for regression, and it models decision using a tree structure. So talking about a tree now, we have nodes, well, which represent decision points or tests on features. Then we have branches also like outcomes of these tests. So it's more like what you have in in a normal flow chart for an algorithm, right? If this holds, then do this. If it doesn't hold, then do that. That's that kind of thing. So we have branches which talk about outcomes of this test. And we have leaves or terminal nodes. These are final predicted labels or classification or values. That's in the case of regression, but here we're talking about classification. So they mimic human decision making, making them highly interpretable and intuitive. Now let's talk about tree construction. So, first of all, recursive partitioning. This starts with the entire data set. So you have the whole data set that can be considered as root node. And then you can select the best feature to split the data into subsets that are more pure or homogeneous in target variable. Then you split the data set based on this feature. Then you recursively apply the same process to each subset until a stopping criterion is met. E.g., you need pure nodes or maximum depth. That's maximum depth is something like half the furthest you can go. Then we have splitting criteria too. So here you choose the best feature to split the best feature to split, which involves evaluating how well a split separates the classes or predict outcomes. So common metrics for this include entropy. Of course, we know the idea of entropy in chemistry talks about disorderliness, right? So entropy and information gain, this is explained after now. Watch out. So we have Gini impurity, which is used in the CART algorithm, and we also have gain ratio, which adjusts information gain for bias toward multi-valued attributes. So we talk about entropy and information gain. Entropy measures the uncertainty or impurity or disorderliness of a node with respect to the target classes. So for a node T with classes C1, C2 up to CK, for instance, entropy H of T is defined. This is the Shannon. This is something from Shannon that measures entropy. So, and this has a whole lot of applications, right? In information theory, it has application in even ecology, right? It's used for diversity measurements in ecology, for instance. So here H of T is equal to minus summation from I equals 1 to k of pi log to base 2 of pi, where pi is a fraction of samples in class I at node T. So that talks about uncertainty of a node with respect to the target classes. So we need to take note here that if the node is pure, meaning that all samples belong to one class, that means that if all samples belong to one class, then entropy is zero. That is, there's no uncertainty. Maximum entropy occurs when classes are evenly distributed. So when classes are evenly distributed, we have maximum entropy. Then we also talk about information gain for decision trees. So information gain energy measures the reduction in entropy after splitting the data based on an attribute A. So you have information gain for D, comma A, that is H of D minus summation over V of which are values belonging to A. So absolute value of dV over D, HD of V, where H of D is entropy of the data set before the split. dV is the subset of D for which attributes A takes the value V, and values A set it takes the set of all possible values of attributes A. So you want to choose the attribute with the highest information gain to make the best split. So that talks about some kind of math that goes in the background, but most of the time we just see the codes and how they perform. And we have other criteria in brief, like we have Gini impurity. The Gini impurity, for instance, is Gini of T equals 1 minus summation from 1 equals I to K of Pi squared. So I believe the Pi here should still be that fraction of samples in class I, right? So this measures the probability of misclassification, and lower is better since it is measuring probability of misclassification. A lower probability tells us that you have less of not very low misclassification. Then apart from Gini impurity, we have the gain ratio, and this adjusts information gained by the intrinsic information of the split, and it helps to avoid bias towards attributes with many distinct values. So let's talk about stopping criteria and overfitting. Okay, so decision trees can grow very deep, perfectly classifying training data, but overfitting and performing poorly on unseen data. So common stopping conditions would include when no display or all samples belong to one class, no remaining attributes to split, maximum tree depth is reached, minimum number of samples required to split or remain in a leaf node, minimum information gain threshold is not met. So these are some stopping criteria actually. So we talk about pruning. Pruning removes parts of the tree that do not improve generalization, right? Generalization, reducing overfitting. So we have pre-pruning, that's early stopping. So you stop tree growth early if number of samples in node is below threshold or depth exceeds maximum allowed. So if you want to go a depth of 3, after 3, even if you have other things to do, you can't go further. Then you can have information gain below threshold for early stopping. But you can also have post-pruning, that's prune after full growth. So grow full tree without restriction, that's post-pruning. Evaluate impact of removing subtrees on validation set. Then remove subtrees that do not improve or hurt validation performance. So common post-pruning methods include reduced error pruning or cost complexity pruning. That's minimal cost complexity pruning used in scikit-learn. So let's talk about decision tree algorithm summary. Um, First of all, we calculate entropy of current data set. That's the degree of disorderliness, right? And then for each candidate's attribute, you calculate information gain. Then you choose attributes with highest information gain for split. Then split data set by attribute values into subsets. Then you repeat recursively on each subset until stopping criteria are met. Then assign class labels at leaf nodes. Okay, so now let's take something practical now, talking about writing codes. Okay, I think it's always good to have the lines numbered for easy referencing. So build and visualize decision trees. Now let's see a very good example. We are still using the iris dataset classification. So we want to classify the iris dataset. You remember when we used iris dataset for k k nearest neighbors, for k equals 3, we discovered we had a perfect accuracy, which is which, well, it's understandable because the iris dataset is very well, the structure is pretty simple and there's no complexity, and we can even say there are no interactions per se, right? So here for this now we need to uh of course we need to load the iris dataset. So from scikit-learn dataset import load iris, then scikit-learn.tree, since we're talking about tree now. So you discover that most of the times the model we are going to use comes at a layer like this. So we import decision tree classifier. So the other time we used k neighbors classifier or something like that. Then we have a plot tree. Then from sklearn model selection, we of course we need the train test split function to partition our data set into training data and testing data. So again, we load the data set. We say iris is load.iris, and from here now, this one, in scikit-learn, the data sets have been so made in such a way that instead of having to worry about having rows and columns and the names and everything, it's not necessary because they have been so arranged that you have the features already partitioned, and you have the target also separated from that. So usually to get this from the iris dataset here, you have the X. Now we talked about the features. You get that from iris.data, and Y is iris.target, so you can then split into train and test sets. So you have, this is a standard kind of statement. So for every kind of model, this is always useful. Like we've seen it for even that snippet on linear regression, we've seen it for nearest neighbors. Now we're looking at it, the same thing for decision trees. So where you have X train, X test, Y train, Y test, and that is equal to train test split, then X comma Y test size. Now here we're using test size as 30% instead of the 20% we've been using before. So you can vary this to see which one gives a better result, right? So, and then the random state equals for the to tell is there to help us maintain the result that you don't get, the result don't keep changing each time you run the code. Then the next thing is to create decision tree classifier. So you just say CLF, you can call it anything. But here we call it CLF, and then that is decision tree classifier. This is where the model itself is coming in, line 14. So the criterion is entropy. Maximum depth is 3. You can vary this to see what happens. So that means that maximum depth is 3 for pruning. So anything beyond 3, we don't go further. And then we have CLF.fit. X train, Y train. So this line 15 is where the real action is taking place. So once that is taken care of, then you can go and evaluate the accuracy. So you want to print the accuracy. So for the model now, you just say CLF.score. So here you want to do score for decision trees. So you have X train, Y train to two decimal places. Then you want to print the test accuracy also, which tells us the overall performance of the whole thing. All right, also in two decimal places. Then you can now visualize the tree. So you say plot figure 12 by 8, tree. So the CLF, that's the decision tree classifier. Then the feature names, you have iris.feature names, class names, you have iris.target names, and field true, rounded true. Then plot title, decision to visualization, maximum depth is 3, and then you can show this. So if you run this now, we get something beautiful jumping at us. Yeah, so it's still running. It takes okay, yeah, it's out now. So you see the accuracy is 0.95. That's very high. The test accuracy, training accuracy is 0.95, test accuracy is 0.98. So it means that the model performs very well with the training and the test. Now, overfitting would have occurred if the training accuracy was 0.95 and then we now had test accuracy to be like say 0.6. So that tells you that you had overfitting in the model. So the model is good for the training set, but then it doesn't perform well with unknown data, so to speak. And that's where overfitting comes in. Okay, now look at what's happening here. So imagine this decision tree visualization for maximum depth of 3. So it means that so for this now, if you look at petal length in centimeters, less than 2.45, the entropy is 1.5. With the samples, 105 of them, you have the values 31, 37, 37, and the class is versicolor. So if this is true, then you go here, entropy is 0.0, sample is 31, value is 3100, and the class is setosa. So we leave that there. Then false. If this is false, then you go petal length is now less than 4.75. So you do this further. So this is like an end. I think there's a word for that. Like it has reached the so it's like a terminal node. It's not a leaf, right? It's now a leaf. It has reached a terminal node. So you don't go beyond that. Once you reach an entropy of 0, that's like the end in that regard or something. Okay. So here for petal length, entropy 1.0, sample 74, class. Of course, since this one has been settled here, so you have 0, 37, 37, and then the class is versicolor. So now so this there's no true or false, so this has two branches now. So here you have petal with less than 1.6, you have the entropy 0.196, samples 33, and here it's 41, and petal length here is less than or equal to 5.15. So the value is all the 032 1, and here is you have 0536. So versicolor, virginica, and then these two can still go on, and it keeps going like that. So that's an idea of how the classification thing goes, like that. Okay, so at the end of the day, you have all these ones where entropy is 0. That those are like terminal points that you get to, like that. Okay, yeah. In fact, yeah, even this is 0 like that. But because you cannot go beyond maximum depth of 3. Okay, in fact, let me change this maximum depth to say 4 and see what happens here, you know, because I actually believe that you could go further at some point. Okay, this is not working so well. So we have this from here. This keeps going. So each tree can go as much as 4. So it gives a new kind of uh thing like that. and we have that. So you can play with the maximum depth to see how far that goes. So let's leave this at 3 for now. So, but overall, we can see the model performance is very good on the training set, 95%, test accuracy 98%. So the explanation here is that we use the entropy as a splitting criterion. Okay, so you see, this is why we do this here. We use entropy as splitting criterion. So you can have others like we saw before. Then the maximum depth is 3, which limits the depth. That's for pre-pruning now. So after training, accuracy on train or test sets is printed to check for overfitting. So like I explained before, if the accuracy for train is so high and then it's higher than accuracy for test, then you can know that's overfitting already. Then plot tree visualizes splits, features, thresholds, and class labels. So that's what you're seeing in all these places in this whole decision tree we have here, so that um then we can talk about the interpretations and limitations. So for the interpretation, decision trees provide explicit rules for classification or regression. So each path from root to leaf represents a decision rule, e.g., feature 1 is greater than 5 and feature 3 is less than 2. Then class is X, like that. Visualization aids understanding and communication. So if you look at this, you can actually follow how the whole classification thing is going, right? So we can see the decision tree going on like that. So for the limitations, so it tends to overfit without pruning. If there's no pruning, you can have overfitting. Small changes in data can produce very different trees. So there's high variance. It may create biased trees if some classes dominate, then less powerful compared to on some methods. So on some methods are methods that combine trees together. Where, for instance, you have random forest and gradient boosting. I think after decision trees, we'll be talking about random forest most likely. So the interesting thing is that just like k nearest neighbors, decision trees can also be used for regression. In that case, you'll be getting values, not classifications, most likely. So summary, uh, for tree construction, you have the description, you have recursive splitting using best attribute based on criteria. Entropy is measure of disorder, and it is 0 when you have pure nodes. Information gain talks about reduction in entropy to select best splits, and pruning talks about techniques to reduce overfitting. So you have early stop or post prune, and visualization, that's graphical tree, helps interpretation and debugging. Thanks so much for listening. Let me know how helpful this is for you, and if there's something you'd like me to try. If you have not subscribed, please feel free to subscribe right away and hit the notification bell too, so that you can always get alerted each time a new video is released. And my channel now has membership, my YouTube channel. You can be a member of my channel to get special privileges like having a badge next to your name, or getting my PDF math notes on request, or having one-on-one consultation with me. It all depends on the category you choose to join, right? So be sure also to share, to like and share, this video, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing data right. Bye.